So the other two models that we've been talking about are density-dependent growth and density-independent growth. Both of those models assume that as soon as an organism is born, it gives birth. In other words, to make those curves smooth, you've got to assume that there's instantaneous birth and death rates and reproduction. It's not entirely realistic. You need to have a continuous function in order to really be able to do some interesting math. Now, that's not entirely realistic. All members of a population don't necessarily contribute to population growth in the same way. So if you think about a long-lived an animal like a giraffe, where there's a great deal of time to maturity, then that population is going to act differently depending on which different pieces of the population or members of that population are more numerous at one time or another. So what we're going to look at is what's called age-structured growth. And now we're looking at cohorts. Cohort is just a group of individuals followed from birth to death. For this kind of study, what happens is that a researcher will go out and look at a group of animals all born in 1 year. And then they will follow that group or that cohort through the rest of their lives, counting their numbers, looking at mortality, looking at reproduction at different ages. So it is going to get a little hairy with the math. It's very simple math, but it's a lot of numbers. I just want you to try and understand what they mean. So let's look over here at age class. Now, what we're calling our age classes, we don't say ages, because the age class could be all individuals from 0 to 1, all individuals from 0 to 2 years old, etc., etc. It depends on the life of the organism. I mean, if we're going to be talking about something like a sea turtle, we're going to be looking at decades instead of looking at years. Similarly, if we're talking about bacteria, this age class might be a matter of hours instead of years. And so that's why we call it age class. Now we're going to enter a variable here, x. So all that means is that whenever you see the x, it could be any one of these numbers. That's why it's called a variable. Then we're going to look at the living cohort, or the survivors. Who's alive at each age class? So we're going to name it S of x. And so that's the number of survivors at each age class. So S of 0 is going to be 500. So we're going to assume for this organism that 500 individuals are born. And that's our beginning of our age classes. At age class 1, we're going to assume that 400 individuals were born. That means that 100 individuals died in between these two age classes. In age class 2, there's only 200 individuals. So now 300 have died from the original. Age class 3, only 50 are left, and in age class 4, everyone's dead. So now we're going to look at the number, or the number born per individual. So when we're dealing with these kinds of equations, generally if it's a capital letter, it means the number of. If it's a small letter, it means the rate, or it is the number by some parameter. Here it's number born per individual. We're going to call that B of x. Again, this is a measured item. We've measured this and we've measured this, so they'd be given to you on any life history table. So the number born per age class. Well, when they're all born, they're not mature enough yet, so they don't have any reproduction. At the first year, they each have 2 offspring. In age class 2, they each have 3 offspring. Age class 3, they have 1 offspring, and age class 4, they have 0. Because they're all dead, they can't reproduce. Now, I want to point out here that if I were going to look at these numbers and say I was responsible for managing this population, and it was an endangered population, and I only had money to actually protect one age class, and that's because each age class has maybe a different environmental need. Well, if I just looked at these numbers, I would say, oh, look, I'm only going to protect the second age class because each individual has 3 offspring. In general, these tables only represent females, partly because with females, we know that they are giving birth. You really have a hard time. It's hard to tell paternity without genetic tests. We're going to calculate another number here, the percent surviving. We're going to call this L. That's an L. L of x. And so L of X, what it basically means is how many survive from one class to another. And so here 500 are born. Well, we're in the 0 age class. 500 out of 500 is 100%. So in age class 1, only 400 out of the 500 survive. So that's 400 divided by 500 equals 80%. In second age class, 200 out of the 500 survive. So only 40% of the original are surviving to this age. And in age class 3, they're getting kind of old, so there's not many left. There's only 50 out of 500, or only 10% are left. And in age class 4, they're all dead. This column is going to represent the actual number born that year. And so what it actually is the birth rate per individual discounted by the percent surviving. This birth rate is when we go out and we measure all the individuals that are left in the population and we look at how many offspring they have. But what we're not taking into account is that at some ages we have actually pretty high mortality rate. So we want to actually handicap this by the mortality rate. So what we're going to do is multiply this column and this column, L of X times B of X, or the number born times how many actually survive. It's like taking a weighted average. So if we multiply these two columns, again, when you're born, nobody's having any offspring. Even though 100% survive, they're not reproducing, they're not mature enough. In the first age class, so only 1.6, if we discount by that 80%, we multiply 80% times 2, they're actually 1.6 offspring born per female in that given age class. And so you can see that this number is less than the 2, and that's because not all 500 are alive. Only 400 of the 500 are alive. What this number actually represents is how much is this particular age class contributing to the population growth of the population. And so it's not 2, right? It's actually less because some die. Again, if we do it here, we have 3 individuals times 40%. Only 40% or less than half are alive. So instead of 3 now, what they're actually contributing is just 1.2 individuals per female. And that's because most of the females are dead. And in this age class, only 1, but there's only 10%. This one's not contributing very much to the population at all. And that's 0.1. What this tells me here is that if I were going to actually do any kind of conservation on this species, I might be fooled into looking at protecting age class 2 because there's more born. But there's so few of them compared to age class 1 that actually this age class is contributing more to the growth of the population than this class. And so what I really should do is concentrate my conservation efforts here instead of here. Now your book is going to go into different categories that they think are important. These are the ones that I find important because these are the ones that are important for conservation and management of species. If you were to add this whole up, you would actually get the rate of growth. And that rate of growth would be centered around 1 instead of 0. So if it's more than 1, you have a positive rate of growth, and less than 1, you have a negative rate of growth. That's not so important. The reason for that is now we're looking at discrete populations, which means that each age class has a beginning and an end. We're not looking at a continuous function anymore, which is why we're not looking at graphs. So if you had to create a conservation plan that could only target one of these age classes, which age class would you focus on? Well, I would actually focus on this one. And for an exam, this might be a question I would ask. I would probably give you the entire life table. I wouldn't ask you to compute anything during an exam, but I would give you this life table and I might ask you a question like, so which age class is contributing most? And you would say, oh, actually it's number 1 because more of them are surviving in that age class. Even though each individual is having more, there are fewer individuals in that age class. Which leads us to the idea of survivorship curves. And I just want to say survivorship curves are a gross generalization. They're being, we teach them because we like to put things in categories, but I have to say that these are very much a generalization, and it can give you some insight into the population. So what we're going to do is graph this number right here, the L of X. So we're really just looking at the survivorship over time. So here we have the proportion that survived to each age, or L of X, by the age, or the age class. And what we find is that there's different kinds of survivorship curves. Survivorship 1 or type 1 survivorship curve typically have a very long, right here is very long survivorship at young ages and dropped off dramatically. It's not the best picture. Your book does a much better job. But it should have a very long survivorship at young age classes, followed by a precipitous decline at older age classes. So these are going to be organisms that generally are long-lived. They're organisms that have very few young and put a lot of effort into parental care. So that's why you have such high survivorship here, because the parents are making sure that those few offspring they have are actually surviving long. These will be what are called K-selected habitats. These are going to be organisms that undergo usually logistic growth. These are organisms that, and we talk about life history characters, these are going to be those organisms that have few young, that are iteroparous, but have high parental care. That's kind of their strategy. Type 3 survivorship is the complete opposite. These are going to be organisms that at the lower age classes, they have a really steep mortality rate. So mortality goes down very big right in the early age classes. But if you make it through there, you pretty much go steadily until your death. These are going to be organisms like insects, invertebrates, flowering plants, any organism that has a lot of offspring, right? But they don't take care of them at all. And that's a different strategy, right? That's the semmelparis strategy, or the strategy in R-selected habitats, populations with exponential growth. And so the idea here is a population that's limited only by its ability to reproduce, right? Not competition. And so in this case, you're going to get a high mortality at young ages, but you're going to have a lot of offspring, and at least some will survive. And I do want to stress that neither one is better than the other. Like, there's situations where one's better than the other, of course, but they're two different ways to get to the same place, and the same place is fitness. You want to maximize your fitness. You can either do it by having a lot of offspring and not taking care of them and dying, or you can have just a couple offspring and really take care of them and make sure they survive. Type 2 is kind of the one right in the middle. It's just a linear function. Each age has the same chance of survival or chance of mortality. This one's not as common. We don't really think of it very much. We just put it here for completion. Maybe some birds, buried seed banks. Once a seed is buried, it's not really vulnerable to being eaten by rodents. And so every year, just the chance of mortality is just as the same as it was the year before. So here's just the survivorship curves one more time. Here, early loss, low parental care, high survivorship early age classes, but late loss, more like humans, and then constant loss. And here it just gives you a hydra, invertebrate. So survivorship curves actually can vary greatly with the environment. These are two species of impatiens, and they're in different habitats. They're different populations. This population has a type, this looks more like the type 3 survivorship, where there's a lot of survivorship and then whoosh, right down. This one has a more steady. And what you get in here is these difference between these two populations of very closely related organisms, I mean, it's the same species, just different populations, is that there's a specialist herbivore, pardon me, and that can really change your survivorship curve. And then it can actually have dramatic effects on life history. So this whole unit has been about life history and population growth and how populations behave. So keep all of that in mind when we're talking about it, because on your exam, we're actually going to mix it all up. And I'm going to ask you questions that cross over all of them. And I'll give you practice at the end of this lesson. One thing you can get from looking at these survivorship curves and looking at age-structured population is what we call a stable age distribution. And so I just put this up because this actually is a conservation strategy. This is an animal, the ibex in the Italian Alps, that was hunted nearly to extinction, and then it was protected. So after it was protected, we can see that there's different age classes. And so this just shows you how many individuals are in each age class. And you see over time that it's changing a lot. And that's because the population is still growing. And once those numbers kind of even out and we have the same relative number of individuals per age group, we say that population is stable and recovered. So this is one way that we use this in conservation.